Okay, so let's look at income tax, okay, and we'll do by example. A woman paid 6,600 euros in income tax for the year. She had a tax credit of 4,600, standard rate cut-off of 28,000, a standard rate tax was 20% and the higher rate was 40%. Find her gross tax for the year, find the income tax paid at standard rate and at higher rate, and how much income did she earned in excess of 28,000. Okay, well, the way to do these problems always is to start by drawing our values sheet. Okay, so it always looks like this. Okay, the gross pay goes here, that we get 20% of the salary up to the cut-off here, we get 42% of from the cut-off to the final salary here. This is always the gross tax, this is always the tax credits. This minus this gives us the tax payable. The gross minus the tax payable gives us the net pay. Okay, so shrink this a little bit, and we can see that the woman paid 6,600 income tax. That goes in here, okay? And she had a tax credit of 4,600. That goes in here. And we know that if this minus this equals that, this must be equal to the sum of these two, 11,200. Okay, and then she had and a standard rate cut of 28,000. So 20% of 28,000 is 5,600. Okay, and this plus this must be equal to that. So this is also 5,600, and this is where it might get a little bit tricky for you, but if you go back to those, I think it was the type 2 percentages in Arithmetic 1 video, we should know that, just bear with me a second now, yeah, sorry, in this case, this is 40%. Some examples it's 42, some it's 40. In this one it's 40%, okay? So 40%, this value here represents 40% of the balance between the cut-off, which is 28,000, and what they finally earned, okay? And 40% of that balance is 5,600. So 1% must be 5,600 over 40, and 100% of the balance from the 28 up to the final salary must therefore be equal to this times 100, and we see that's 14,000. Okay, that's the income in excess of 28,000. In other words, 40% of 14,000 is 5,600, and if that's the case, we then know that this person actually earned 28,000 plus 14,000, 42,000 euros. Let's look at compound interest. So here we just need to be aware of two things: that the interest amount, in euros or whatever it is the final amount minus the principal amount. So in other words, a person has 100 euros, they put it in the bank as a principal amount at the beginning of the year, and they're told they're going to make 5% on it. So at the end of the year, they take out 100 plus 5% of 100 is 105 euros. So the interest amount would be just the 5 euros, the difference between what they put in and what they got out. Okay, and the interest rate is the interest amount divided by the principal, that money they put in initially, and that's by 100. Okay, and that's the interest rate is a percentage. Okay, that's why we multiply by the 100 here. And I suppose a very important formula here then is the compound interest formula, and that tells us that the final amount that someone will receive is equal to the principal that they've put into the bank times this multiplier, which is 1 plus I, and that's basically the interest rate, 1 plus I, which is the interest rate expressed as a decimal, and that multiplier is to the power of t time. So I suppose the best way to look at this is to do by, just look at the example. And just bear in mind that, when someone invests money for 2 years, they put the money in, they make interest in year one, they have a final amount of year one, which goes back into year two as the new principal value. Okay, so let's look at this problem here. 5,000 euros was invested for 3 years at compound interest rate. For the first year it was 4% and the second year was 4.5. Find the amount of investment at the end of year two. So we plug in our 5,000 and the initial interest rate, 1 year, and we find that at the end of year one, 5,200 euros had accrued or was ready to move on into year two as the principal value at a different rate for 1 year. And at the end of year two, that 5,000 euros was now worth 5,434. But at the start of the year three, an additional 4,000 was invested or added to this amount. So the total investment at the end of the year was now worth 9,811 euros 36. What was the interest rate? Well, basically, we put in the final amount plus the initial amount, is equal to the initial amount, which is this plus 4,000 as our principal, all times 1 plus I. So that then means that 9,811.36 divided by 9,434 is actually 1.04. That's equal to 1 plus I. So therefore I must be 0.04, which means that we can say I is 0.04, but as a percentage we multiply that by 100 and we get 4%. Okay? So basically we simply divided this value by this value so that we could get the 1 plus I on its own or isolated, and then we took the 1 over here and away from 1.04 to find our value of I. So let's look at annual equivalent rate, or AER, and just to note that there's 3 types of problems you can meet with the annual equivalent rate. And the first type of problem is to do where you're given a sum of money and a rate, and to find out, what the annual equivalent rate was given that the money appreciated or depreciated. Okay, so for example, find the annual equivalent rate on 120 euros that's left unpaid for 12 months at a monthly interest rate of 3%. So maybe the 120 euros, someone bought something with a credit card and they didn't pay anything off on the credit card for 12 months, and that was fine, but the credit card company were charging 3% each month. Okay, so to find what that 3% that was charged at a monthly every month, to find what that is equivalent to over the year, we first find the final amount owed after 12 months, and we use the compound interest formula for that with the 3% rate here, and 12 as the time for 12 months. And we find that if someone owes the credit card company 120 euros and they don't pay it off they let it run for 12 months at 3% monthly rate, then after 12 months they'll owe 171 euros and 9 cents, not 120 euros. Okay, so now that we know what they truly owe at the end of the 12 months, we can find what's the interest amount, and that's basically the difference between what they now owe and what they owed initially. So that's 17109 minus 120. So the interest that has amounted up over the 12 months is equal to 51 euros and 9 cents. Okay, that's the actual amount. So to find the annual equivalent rate, we put that value over the 120, which was the initial amount, times 100, and we find that actually that's 42.5% interest on the 120 euros. So that's a particular problem which at the end we found the annual equivalent rate by using this formula at the very end. Okay, but we had to find what 120 euros turns into after 12 months at a monthly rate of 3% before we can find out the annual equivalent rate. The second type of problem is to do with bonds, and there's a formula that we'll use. If we see investment bonds, we'll just use the formula. The annual equivalent rate is equal to this multiplier 1 plus I to the power of t for time minus 1. So a bond gives 20% return over 8 years. So over 8 years, a person gets 20% more back than what they invested. Find the annual equivalent rate. So if we got 20% over the 8 years, what was the rate per year that they were getting back annually? Okay, so to find that, we just simply say 1 plus 0.2, which we got from our 20 over 100 is 0.2, or 20% is 20 per 100. So, and our time, we're looking for 1 year of the 8, so it's 1 over 8, an eighth, okay? So it's 1 plus 0.2, all to the power of 1/8, 1 year in 8 minus 1, and we find that that's 2.3%. And the third and final type problem is where of AER problems is where we have credit card charges. Okay, so a credit card company charges interest at a rate of 2.5% per month. Find the annual equivalent rate. Well, we basically use the same formula as we did down here. So we have the same formula here, where we have our multiplier here and the time minus 1. So we'll see that they charge 2.5%, so that's 1 plus 0.025, all to the power of 12, because 12 months in a year, and we find that the annual equivalent rate is 34.5%. Let's look at depreciation. Depreciation problems use the compound interest formula with a minus sign instead of a plus sign. A van costs 15,000 euros new, it depreciated at a rate of 15% per annum. What is it worth after 2 years? Its final value is equal to the principal, the initial value, times the multiplier 1 minus 0.15, which is basically 15%, 15 over 100, 0.15, 2 years, t is 2, so we see that the final value, having depreciated over 2 years, 15% per annum, is €10,837.50. Moving on now to the speed, distance, time type problems. Two types of problems presented in this chapter. One is simply using the formulas. The second type is reading distance time graphs. Well, the formula for speed equals distance over time. The units used mostly in this chapter are kilometers per hour. With that in mind, you need to be sure of how to convert from minutes to hours, or hours to minutes, or fractions of hours to minutes. Okay, so 36 minutes in hours is 36 divided by 60 hours, always. 22 minutes in hours would be 22 divided by 60 in hours. 0.2 of an hour is 0.2 times 60 minutes. And a half hour, or a fraction of an hour, is a half times 60 is 30 minutes. Okay, so there are the formulas to convert over and back. Let's look at an example. Eamon took 46 minutes to jog a distance of 6.4 kilometres. Find his speed in kilometres per hour. They've given us the time in minutes, so we need to convert the time in minutes to hours. 46 minutes is the same as 46 over 60 hours, and that's 0.77 hours. Now, speed equals distance over time. Our distance units are kilometres, our time units are in hours, so 6.4 by 0.77 is 8.31 kilometres per hour. Okay? And the last part of this chapter then was to do with distance versus time graphs. Okay, so we get these plots of distance versus time for example, a person cycling to work, jumping on a train, getting the bus back, and so on. And the thing to note is with these graphs, when we have a straight line rising like this, that indicates a steady average speed, which is calculated by finding this value and dividing it by this value, the distance over the time. We see here that there is no increase in distance. It's like a flat line, but time has passed, and that tells us that the person is at rest, hasn't moved. Then when we look at the graph, we see that there's a steady rise in the graph again, and this time we can calculate the average speed between this time and this time here by finding the difference in the distance travelled over the time taken. So again, it's the distance over the time on the graph, reading between the 2 points. Okay, so there's your distance change over that time. Speed equals one value over the other. Okay, and it doesn't matter that it's now going this way. It's the same thing. Speed equals the distance over time between time values here and the distance values there. Okay. And also to note, if we're given a graph that is something like this, then the total distance, this is distance time, the total distance travelled is this value plus this value, okay, and we see that they're returned here again, so it's this value plus this value plus this value here. They've gone all the way to a certain point, a distance of, could be, say, 50 kilometers, but then they've gone another 50 back. Okay, so for this example, if that was 50 kilometers on our distance, they would have travelled 100 kilometers in total to here and here, plus the final 50 back.